Welcome to part 2 of our problem-solving series on the Pythagorean Theorem. Today we'll tackle a fascinating geometry question involving an equilateral triangle and perpendicular lines from a point inside the triangle. Let's begin. Here's the question. Point P lies inside equilateral triangle ABC. From point P, perpendiculars are dropped to each side. PD is perpendicular to BC. PE is perpendicular to AC, and PF is perpendicular to AB. We are asked to find the value of the fraction PD plus PE plus PF divided by BD plus CE plus AF. Let's start with a geometric idea. Draw lines through point P that are parallel to the sides of triangle ABC. This creates 3 smaller equilateral triangles inside the original triangle. If we rearrange these triangles into the corners, their combined heights give the height of triangle ABC. So the sum PD plus PE plus PF equals the height of triangle ABC. Now let's use an algebraic method to compute PD plus PE plus PF. Assume each side of triangle ABC is 2a. Then the height is square root of 3 times a. The area is 1/2 times 2, a times square root of 3a, which equals square root of 3 times a squared. Now divide triangle ABC into 3 parts. Triangle PAB, triangle PBC, and triangle PCA. Each triangle has base 2a and respective heights PF, PD, and PE. So the total area becomes a times the quantity PD plus PE plus PF, which equals square root of 3 times a squared. Solving for the sum, we get PD plus PE plus PF equals square root of 3 times a. Now let's move to the denominator. Let BD equal x, CE equal y, and AF equal z. That means DC is 2a minus x, EA is 2a minus y, and FB is 2a minus c. We'll now apply the Pythagorean theorem in triangles involving these segments. From triangle PBD, we get PD squared equals PB squared minus x squared. From triangle PCD, PD squared also equals PC squared minus quantity 2a minus x squared. Equating gives PB squared minus x squared equals PC squared minus open bracket 2a minus x, close bracket squared. That's equation 1. Now from triangles PCE and PAE, PC squared minus y squared equals PA squared minus open bracket 2a minus y, close bracket squared. That's equation 2. From triangles PAF and PBF, PA squared minus z squared equals PB squared minus open bracket 2a minus z, close bracket squared. That's equation 3. Add all 3 equations together. The terms PA squared, PB squared, and PC squared cancel out. We are left with x squared plus y squared plus z squared equals open bracket 2a minus x, close bracket squared plus open bracket 2a minus y, close bracket squared plus open bracket 2a minus z, close bracket squared. Expanding and simplifying, we eventually find x plus y plus z equals 3a. That gives us the denominator. Let's now look at method 2, a second way to show that x plus y plus z equals 3a. Start with triangle PBD. PB squared equals PD squared plus x squared. From triangle PBF, PB squared also equals PF squared plus open bracket 2a minus z, close bracket squared. Equating both gives PD squared plus x squared equals pf squared plus, open bracket 2a minus c, close bracket squared. That's equation 1. From triangles PAF and PAE, PF squared plus C squared equals PE squared plus open bracket 2a minus y, close bracket squared. That's equation 2. From triangles PCE and PCD, PE squared plus y squared equals PD squared plus open bracket 2a minus x, close bracket squared. That's equation 3. Now add all three equations. We get simplify both sides. After canceling, we get 12a squared minus 4a times quantity x plus y plus z equals 0. So once again, x plus y plus z equals 3a. Now we put everything together. The numerator is PD plus PE plus PF equals square root of 3 times a. The denominator is x plus y plus z equals 3a. Therefore, the entire expression becomes square root of 3a divided by 3a, which simplifies to square root of 3 over 3. The final answer is square root of 3 over 3. Two different methods, one geometric and one algebraic, lead us to the same elegant result. Thanks for watching. If you enjoyed this walkthrough, please like, comment, and subscribe. See you in the next math challenge.